In this playlist, we're gonna put everything we have learned in the second playlist in a more cleaner notation. First of all, let's define a new symbol. It looks something like this. It's called a kit. So the kit of A is nothing but a vector with n dimensions. So we have A1, A2, A3, all the way to A sub n. The inner product between two vectors called bracket. So the first half of this inner product is the bra and the second half is the kit, and is defined as the multiplication of two vectors. So we have A1 complex conjugate. So the first member we always complex conjugate the first member of this inner product times B1 plus A2 complex conjugate times B2 plus all the way to A sub n complex conjugate times B sub n. However, if we multiply a matrix times the inner product, we get a bra. So the bra of beta is nothing but a matrix times the kit of alpha, which is defined as T11, T12, all the way to T1n. Then here we have T21, T22, all the way to T2n. Then here we go down all the way to Tn1, Tn2, all the way to Tnn. So this is n times n dimension matrix times the vector alpha, which is A1 times A2 all the way to A sub n. The product of those is this bra over here. It's important to mention that the integral of the probability density psi star psi dx, this must equal to 1, remember from the previous videos. Alright, so the wave function psi must be normalized, right? The set of all square interval functions on a specified interval v of x, I mean f of x, okay, such that the integral from a to b, let's keep everything general at the moment. In our case, is always going to be between negative infinity and infinity. We always integrate over all space times the probability density of this f of x function dx. This must be less than infinity. And this square interval functions consist of a vector space, okay? We call it the Hilbert space, okay? So we call it the Hilbert space. And in our case, wave functions always live inside this Hilbert space. It is very important to recognize that wave functions, so these are the psi's, live inside the Hilbert space. Alright, so now the inner product of two functions f of x f of x and g of x, we defined this. This is very, very important. So the inner product between f and g is defined as the integral from a to b of f of x complex conjugate times g of x dx. So the bracket, or the inner product, of these two functions is nothing but the integral from a to b of f star times g dx. So this is going to be very, very important. Alright, so if we take the absolute value of this inner product, from a to b, f star times g dx, this has to be less than or equal of the square root of the integral from a to b from the probability density of f dx times the integral from a to b of the probability density of g dx. There's going to be very handy relation between the absolute value of the inner product and this. And in the next video we're gonna prove this. So if you want, you can click at the top right hand corner to see why this is true. Another important thing we need to know, that the inner product of g and f is equal to the inner product of f and g complex conjugates. So this is another important rule. And another important rule, that if we have the inner product of two functions f sub m and f sub n, this is equal to the Kronecker delta m and n. Alright, so finally, the set of functions is complete in any other function in the Hilbert space, can be expressed as a linear combination of them. Mathematically, this means that if the function f of x, this function lives in the Hilbert space. This function can be expressed in terms of a linear combination of c sub n, f sub n times x. Of course, n goes from 1 to infinity. Alright, so now since we have these rules, we can do some physics. Oh, I also forgot to mention that this c sub n, the coefficients, are the inner product of f sub n and f.